Alright guys, so I want to do a tutorial about the basic differentiation rules we've covered so far in the course. So here you see a list of the ones we're going to cover in Chapter 3. So we have, looks about like 24 different ones here that we'll just more or less have to commit to memory. Now a lot of these are very trivial. A lot of them there's not really a whole lot to memorize. But some of them are more difficult, when you get down here to the inverse trig functions and whatnot. So keep this in mind. That's a pretty big list. But I want to just do a lot of examples, and I'm going to start easy and then go to hard. So notice here, these, and that's generally the order that the numbers are listed in. This is the constant multiple rule, which says that if you have a constant c times a function, and you take the derivative, you can essentially factor out the constant, take the derivative of the function, and then multiply and simplify as needed after that. Okay, so let's look at a couple examples. So I'm going to start off easy. Let's see here. Let's say that. Let's say f of x equals 12. Now, what applies here? I think if we go by this list here, c is a constant. Okay, u is a function, v is a function, c is a constant. We'll have a few more letters when we get down here to logarithms. But for right now, we have u, v, those are functions, and c is a constant. This right here says the derivative of a constant is 0. So if we have f of x defined as so, then the corresponding f prime of x is 0. Now we can show that's true using the definition if you really wanted to, the limit definition. But at this point, we can just say if there's a constant, the answer is 0. Now, the constants could look a little weird. Let's say f of x equals pi. Pi is just a constant. Okay, so the derivative, f prime of x, in this case, is still 0. Even though it's not a number it's not an integer like we're used to dealing with. That's an irrational number. The pi is the ratio of a circle's circumference to its diameter. Okay, but it's still a constant, so the derivative is 0. Now here's one I put on a test one time. This really tripped people up. F of x equals let's say to the 5th power. Now, we are very used to seeing the function f of x equals e to the x. But what is e? Don't forget what e is. E is just a number. If you type into your calculator, let's see here. It's 2.7 and change. Let's see exactly what it is. E is, well, not exactly. This is going to be an approximation. But E is 2.7182818828, so forth and so on. It's just a number. Okay? E is just a number. This is just an e to a number raised to the 5th power is just a number. It's a constant. Okay? So this right here, even though it looks very, very, very similar to a function, this is a constant, so f prime of x is 0. Okay? All those are constants, so all the derivatives are 0. Even the ones that kind of look funny, we think of constants being 1, 2, 3, 5, whatever, 12. But even when the constants look funny, just remember that. You might have constants that, if you're not paying attention, looks like a function. Like I had a lot of students say that the derivative of this guy right here was e to the 5th. Now, if it was e to the x, that would certainly be the case. Because you notice here, over here, let's see. Well, here's like the chain rule version of derivative of the exponential. But the derivative of e to the x is e to the x. But the derivative of e to the 5 is not e to the 5. Okay? Because that is a constant. And the derivative of a constant is always 0. That's a constant function. It just looks like an exponential function. That's a constant function right there. So be careful. Don't miss out on easy ones on the homework. Don't miss out on easy ones. Here's another one. F of x equals cosine of, let's say pi over 2. Now, we're used to dealing with cosine. Let me fix that too real fast. Over 2. We're used to dealing with cosine as a function. Okay? But what is cosine of pi over 2? Oh, let's make it more interesting. Pi over 4. But what is the cosine of pi over 4? Well, cosine of pi over 4 is square root of 2 over 2. Go back to your unit circle. It's square root of 2 over 2. So even though this looks like a function, it's actually just a constant because cosine of pi over 4 is square root 2 over 2. So f prime, the derivative, no, not of 0, of x equals 0. Okay? So be careful when things look like functions but are actually constants. If it's a constant and you're taking the derivative, it's going to have a derivative that's equal to 0. Okay? Let's go a little bit harder. Let's see. What about f of x equal to, let's see. Let's do a power function, or a power of x. 3x squared. 3x squared. Now, there's a few things going on here. We have a constant multiple, a constant times x squared. So what we can do, according to the rules over here, the basic differentiation rules, we can say that f prime of x equals 3 times the derivative of x squared. Okay? We can use the constant multiple rule to essentially factor the 3 out and then take the derivative of x squared. So this equals 3. Now what's the derivative of x squared? The power rule says that you take the original power of x, write it in front of x, multiply by x, and then raise x to the n minus 1, in this case 2 minus 1 power. So we have 3 times 2 times x. Now what's the 2 minus 1 power? It's the first power. Or we have 3 times 2 is 6 times x, so 6x. Now, once we do a whole lot of these, we won't necessarily have to write all these steps out. Now, if you want partial credit in case you make a mistake, you're probably going to want to write these steps out. But at some point, eventually, we'll get to the point where we can just look at this and say, yep, the derivative of f of x is 6x. But if you're on a test or on a formal assessment, you probably want to show work in case you make an arithmetic, algebraic, or maybe a calculus type error, so you can get partial credit, depending on the severity of your mistake. Okay? So in this, we had to use the power rule and the constant multiple rule. Okay? Let's look at a polynomial. Let's go over here. Let's say f of x equals 1/2 x cubed plus 2x squared plus 3 over 4x plus, actually, why don't I have these pluses? We need some minus action in here. Minus 6. Now, If you go up here to rule number 2, that's the sum and the difference rule. What that says is, if you have two functions, and this actually holds true for more than two functions, if you have some combination of functions where you're adding and subtracting them together, you can take the derivative of each of those individually. So we can go here, we can say that this is f prime of x equals the derivative of 1/2 x cubed plus the derivative of 2x squared plus the derivative, again with respect to x, of 3 over 4x minus the derivative of 6. Or I could have said plus the derivative of -6. Either way is fine. So I guess, depending on how you look at that, you're half empty, half full kind of glass here, you could take plus the derivative of -6 or minus the derivative of +6. Now, so we can take each of these derivatives individually and then add them and subtract them just like one would expect. So the sum and product rule work out nicely, how you think they might work. Now, when we get to the product and sum rule, product and quotient rule, they don't actually work as intuitively as you might think. Now, they make sense once you look at the limit definition of why they work, but you probably wouldn't guess that to be the case if you're ever guessing what the way to find the derivative of a product or a quotient. So let's see here. Now, what's the derivative of this guy right here? Okay, well, the constant multiple rule says, so I'm going to write out every little step here. It says we can factor out that 1/2 and take the derivative of x squared. Right here, the constant multiple rule says we can factor that 2 out and take the derivative of what was left over, which would be x. Oh, you know what? I messed up there. That's an x cubed. Okay? Let's see. The constant multiple rule says I can factor that 3 over 4 out and then take the derivative of x. And, I can just go ahead and solve that. What's the derivative of a constant? 6 is a constant, so the derivative of a constant is 0. Okay? And now let's evaluate. I think we've gotten to the point where we need to actually just take some derivatives. Okay, we have 1/2. Now what's the derivative according to the power rule? The power rule says, okay, you take the original exponent of x, right, 3, and then times 8x, which is the base, and then to the 3 minus 1 power. Okay, then we have plus 2, power rule again. Power rule says, actually I should probably put some parentheses here, says, okay, take the original power of x, write it out front, then multiply by your base, and then to the n minus 1 power, so 2 minus 1 power. And then we have plus 3 over 4. Now what's the derivative of x? We haven't talked about that just yet. I mean, we have in class, but not in the last few minutes. The derivative of x, you see, let's see, where is it? The derivative of x, right here, rule 7. The derivative of x, the identity function, is 1, which makes sense because the derivative is slope, and the slope of the identity function is 1. Okay? Now let's just do some simplification here. So we have 1/2 times 3x. Oh, let's do a little more simplification. Let's not do one whole another line. Okay? We have 1/2 times 3. That's 3 halves. We have x to the 3 minus 1 power, so x squared. Plus, okay, we have 2 times 2, so that's 4, times x raised to the 2 minus 1 power, or just x to the first power. Then we have plus 3/4 times 1, so 3/4. Minus 0, so there we are. There is our derivative. So when you take the derivative of a polynomial, just take the individual derivatives of each of those terms. That works out nicely for us. Okay? Now, again, this would be every step. Notation is important. Now, I am going to, or maybe you're not even in my class, but maybe your professor, your teacher, your instructor might want you to do every one of these little steps here. So I'm going to try to really do all the little steps out here, just in case you're in a position where you need to show all your work. Now, notation is important, and I generally require my students to show all these steps. Okay? Now, maybe not every one of these is absolutely necessary. Like maybe you could, write this step instead of 2. Write this here right from 1. But the moral of the story is the more work, the better. The less mistakes you're going to make when you try. The less you do in the head, the less mistakes you're going to make. And if you do make an error on an assignment, generally speaking, your professor is probably going to give partial credit. And so the more work you have, the more chances of partial credit are there. Okay, so that's a derivative of a polynomial. Now, so far, we haven't gotten too hard yet. Let us look at a chain rule type situation. Before we do chain rule, now that I have this over here, let's look at f of x equals e to the x. Now remember, if you just have a plain old e to the x, then f prime at x equals e to the x. That's the kind of the crazy thing about the exponential function, is that it is its own derivative. That's crazy, but that's what it is. So like, if you want to find the slope of the tangent line when x equals 1, all you have to do is evaluate e to the first power. So e is the slope of e to the x at x equals 1. It's kind of crazy, but it's kind of cool. Okay? But now let's say we have like f of x equals, I don't know, let's get crazy. Pi times e to the x. Okay, well all you have to do is use the constant multiple rule, which says f prime of x is pi times the derivative of e to the x. Because pi is a constant, it's a constant function, so we factored it out. It's not a function of x. And so here we have pi. Now what's the derivative of e to the x? Well, like I said, the derivative of e to the x is e to the x. Those are really easy ones. Now, let's see here. What about maybe some chain rule type examples? Okay. Before we get to chain rule, let's do like quotient and product rule. Those are good. Now, notice here, what's the product rule? Product rule. Right here. It's because I've scrolled down. I was wondering where everything is. Product rule, right here. If you have two functions, u times v, you take the first times the derivative of the second, plus the second times the derivative of the first. Quotient rule, it's the bottom times the derivative of the first. No, you don't need to say first and second. You need to say top and bottom. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom function minus the bottom function, over the bottom function squared. So let's keep those in mind, and let's look at some quotient rule. Let me change up the colors here. It's going to get a little harder. Okay, let's see here. Let's see. Oh, you know what? Before I do that, let me do something else real fast. So I'm going to go back to this. The mauve color is going to be the easy functions. Okay. What about if we have f of x equals 3 over x squared? Okay. Now you might say, hey, that's a quotient. can't deal with that right now. I said we're about to get to the quotient rule, but we haven't talked about the quotient rule besides just giving the definition. Now, you can do this without the quotient rule by thinking about the rules of exponents. We could rewrite this as 3 times 2 to the negative 2 power. Okay, so being able to convert back and forth between different exponential forms is very important. Algebra is very, very important in calculus. So noticing that we can write this as 3 times x to the negative 2, that's really important because now we can use the power rule. And the power rule says that f prime of x, well, we can use the power rule and constant multiple rule. So we can factor that 3 out and then take the derivative of x to the negative 2 power. Okay? So what does the power rule say that x to the negative 2 power, what the derivative is? It says, okay, you take that negative 2 exponent, the original exponent, write it out front, then write x raised to the n minus 1 power, so negative 2 minus 1. Don't let those negative signs trip you up. It's negative 2 minus 1. Okay, so that equals 3 times negative 2 times x to the negative 3 power. So we get negative 6 times x to the negative 3. And then if you want to, typically we want to write our answers with positive exponents only, which would be negative 6 over x cubed. Okay, so we can use the power rule to solve that. Now, let's say I didn't remember my rules of exponents, perhaps. And let's say I see a quotient. That means I use the quotient rule. So let's solve this exact same problem, except with the quotient rule. So I'll change colors here. Now remember, what does the quotient rule say? The quotient rule says you take the bottom function times the derivative of the top minus the top function times the derivative of the bottom function over the bottom function squared. So we could also say, going here, that f prime of x is equal to, okay, here's the bottom function, there's the top. So it's the bottom function, it's going to be a quotient here, x squared times the derivative of the top, which is 3, minus the top function, which is 3, times the derivative of the bottom function, which is x squared, over the bottom function squared. So x squared squared. Okay? So let's see what that reduces to a little bit. Now, mind you, that is the calculus. Calculus is over. Well, sorry. Calculus is not over yet. We have one more step to do. We're not quite to just the simplifying part yet. Okay. So x squared. Now, what's the derivative of a constant 3? It's just 0. So x squared times 0 minus 3 times the derivative of x squared. Now, the power rule says the derivative of x squared is 2x. And now, what is x squared squared? If you remember the rules of exponents, when you have an exponential expression raised to another exponent, you can multiply the exponents, and so that's x to the 4th power. Now, what I wanted to say earlier, I want to say now, is that the calculus is over. This is algebra class now. Okay? Sorry. I thought I made a mistake somewhere. No, we're good. Okay, so x squared times 0, that's 0. We're left with negative 3 times 2x, that's negative 6x over x to the 4th. Now we need to do whatever simplification we can do. We notice there's 1x on the top, there's 4 x's multiplied together on the bottom. If you remember your rules of exponents, that means we can simplify this to negative 6 over x cubed. Notice, same exact answers. So we could either think for this, and that's honestly, that's oftentimes how a lot of these work. There's different avenues you can take. So we could either use the quotient rule over here in yellow, or we can think about what are the properties of exponents, and then use the power rule and the constant multiple rule. Okay. The thing is, there are so many different situations. You just have to do these problems, get practice in, because there's no way I could ever show you every possible way to do a basic derivative. These go from super easy to super hard. This is just an intro calculus that I'm teaching, Calc 1. We're not going to get to the super, super hard, but we're going to get to some difficult things. Okay? Let's see here. Let's get into the product rule. So we did a quotient rule. Now let's do a product rule. I got some space off here to the side. Let's say that let's see here. What's a good example? Oh, here's a good example. F of x equals 3x minus 4 times x cubed plus 5. Now, if you wanted to, you could FOIL this problem. You could FOIL f of x, and then you would have a polynomial. And remember, the example right above was a polynomial, and you can take the derivatives of those individually if you wanted to. But there's a lot of algebra there. It might be a little bit more difficult. Not difficult, but there's more room for error maybe. I think it would probably be easier just to go ahead and use the product rule. Because the product rule says that if you have two functions multiplied together, to find the derivative, you take, since multiplication and addition of real numbers are commutative, there's different ways you can say it. I'm going to say the second times the derivative of the first plus the first times the derivative of the second. So here I'm going to say x cubed plus 5 times the derivative of the first, which is 3x minus 4, plus, let's see, the first function, which is 3x minus 4, times the derivative of the second function, which is x cubed plus 5. I thought I would have more space. Oh, hopefully I have enough space. Okay, I'll move my equals sign over a little bit. Equals, okay? So we have x cubed plus 5. Now what's the derivative of 3x minus 4? Okay, so the derivative of 3x minus 4, that's a polynomial, or it's binomial specifically. So we can take the derivative of these two things individually. Now, if we wanted to be really pedantic, I suppose we could write out that this right here is 3 times the derivative of x minus the derivative of 4. Or we can just think through it. I don't think it's necessary to show every little micro step here. The derivative of 3x is 3. The derivative of negative 4 is 0. So we could just say it's equal to 3. Okay. Plus, okay, we have 3x minus 4. And what's the derivative of this function here? Okay, we have x cubed. The derivative of x cubed is, according to the power rule, you take the original exponent out front, then you have x to the n minus 1 power. So 3 minus 1 power, so that's 3x squared. And then you have the derivative of 5. Well, the derivative of the constants is 0. So there we are. Now, at this point, is there any real benefit to multiplying? We'll have like terms. If we multiply this out, and we'll have some like terms, so it's probably a good idea to do that. So let's see. We have a distributive property a couple times. So we have 3 times x cubed, which is 3x cubed plus 15. Then we have, let's see, 3x and 3x squared, so that's a total of 9x squared. Then we have, cubed. 9x cubed. Then we have, let's see, negative 4 times 3x squared, so that's minus 12x squared. So let's see here. We have, actually I can introduce back my f prime of x. F prime of x. We have 3x cubes and 9x cubes, so that's 12x cubes. And we have minus 12x squared and plus 15. Okay, which is the same answer we would get if we FOILed this and then took the derivative of that resulting polynomial. Okay, so that's the product rule. Let's see here. Let's up the ante a little bit. Let's see what we can find. Let's throw a little bit in the mix. Let's say we want to. Oh, let's not do that right now. This video is just on straight up finding derivatives. We talked about applications. We'll talk about applications in other videos. Let's just find derivatives this time. Let's see here. Well, let's add some trig functions in the mix. Okay, let's mark that off. Let's change colors. Let's say f of x equals. Let's find a fun one. Let's see. X squared times sine x. Okay, x squared sine x. So clearly we have 2 functions multiplied together here. We have x squared times sine x. We have to use the product rule. Now, don't be tempted to say that the derivative of a product is equal to the product of the derivatives. For instance, we can't say this is equal to, let's say, not equal. We can't say dx of x squared times dx of sine x. It doesn't work that way. Don't be tempted to do that. You got to use the product rule. Okay? Product rule says, it says we can take the second function, which is sine x, times the derivative of the first, which is x squared. Oh, I'm going to run out of room again. Let me back this up a little bit. Equals. It's the second function, so sine x times the derivative of the first, plus the first function times the derivative of the second function. Okay? F prime x. Sorry, I shouldn't have had that equal sign there even to start with. Sorry about that mistake a few minutes ago. F prime of x. Okay. Let's see here. So simplification, or still taking derivatives. What's the derivative of x squared? Well, that's 2x. Then we have plus x squared. What's the derivative of sine x? Now remember, this is just one of those things you need to memorize. The derivative of sine is cosine x. And now, just a little bit of a simplification. I mean, I would write the 2x out in front of sine x. And there we are. We're done. So the simplification there wasn't anything major. Okay? There's nothing really else to do there that's really too productive. So there is another product rule. Oh, let's see about a product rule with a quotient rule maybe with some trig functions. Let's see here. What about if f of x equals, what do we have here? Let's say cosine, no, let's say cosine x over x cubed. Actually, let's say cosine x over x cubed plus tangent x. So here, not only do we have a quotient, but we have a quotient plus another number. So we have a sum of two functions and a quotient over here to deal with. So let's see, f prime of x. Now let's deal with because with a sum of two functions taking the derivative, the derivative of a sum is equal to the sum of the derivatives. So let's deal with the quotient first. We're going to have a fraction here. Now the quotient rule says on the denominator, we know that's the easy part, it's going to be x cubed squared. Now we're still going to have the derivative of tangent x over there, so let's not forget about that. Let's see here. So the quotient rule says we take the bottom times the derivative of the top. So x cubed times, dx cosine x minus the top function, which is cosine x times the derivative of the bottom function, which is x cubed. Now we can go ahead and just take the derivative. Well, I'll write this out. The derivative of tan x. I'm tempted to skip steps just like you are, but you got to resist the urge. Okay? So let's see here. What's x cubed squared? Just like before, I think we've seen, when you have an exponential function raised to another, or an exponential expression raised to another exponent, you multiply the exponents together, and you get x to the 6. Now we have x cubed. Now what's the derivative of cosine? Now the derivative of cosine is negative sine x. That's just one of those things you need to memorize. Then we have minus cosine x. And what's the derivative of x cubed? According to the power rule, we write 3x to the 3 minus 1 power, or 2 power. Now plus, what's the derivative of tangent of x? Now, let's see, if you go back up here, it's one of those things you just need to have memorized. Now, the trig functions, there's a lot of them. We have 6 plus the inverses. But you see here on rule number 15 that the derivative of tangent is secant squared. So, secant squared x. Okay, so we have equals, big old quotient here, x cubed, we can say negative x cubed times sine x minus 3x squared cosine x plus secant square x. And there is f prime of x. Okay? F prime of x. Now, there's not really any benefit to trying to simplify that much beyond there. Okay? Let's see. Harder? What about chain rule? Now, the chain rule deals with the composition of functions. So let's look here. Let's get some little more difficult ones. Okay. Oh yeah. Let's get some. Well, let's have a moderate, and then we'll get to some hard ones. Let's have a moderate one. Let's say Let me change up the color here. Let's go to yellow. Let's say that f of x equals 3 over the square root of x squared plus 1. Okay. Now notice, we have two options here. Well, first of all, let's notice this thing. The first thing you want to notice is that when you have radicals, for at least right now, it's going to be a good idea to immediately think about fractional exponents, because x squared plus 1, that's the same thing as raising to the 1/2 power. When you're dealing derivatives, that's probably what you want to think of always. Okay. Now we have a couple options at this point. Notice we have a quotient. Okay. We can either think of this as a quotient rule type problem, where we have a top function and a bottom function, or we can think about this as equal to 3 times x squared plus 1 to the negative 1/2 power. In which case, we have a situation where we have a constant multiple out front we can factor out, and then we can take the derivative of our composite function using the chain rule. Okay? Neither one of those is right or wrong. I mean, this way is probably faster, but maybe I'll show you both ways. You could also think about this as being the product rule. You could think about this as being the product of the constant function 3 and this function right here. Now that would probably be the most roundabout way to do it, but you would get the same answer. So let's see here. F prime of x. Let's do it the way of using the constant multiple rule. So 3, factor that out, and then find the derivative of x squared plus 1 raised to the negative 1/2 power. Okay, so we have 3. Now, this we can use what's called the generalized power rule, which says you essentially use the power rule as we know it, but then you have to multiply by the derivative of the inside function. So we say the power rule says bring the original power out front, multiply by in this case, our inside function, raise it to the n minus 1 power, so 1/2 minus 1 power. But here's where the chain rule kicks in for the generalized power rule, which says we have to multiply by the derivative of the inside function, which is x squared plus 1. Close parentheses. Oh, that wasn't a good one. Close parentheses. So this equals, all right, what's 3 times negative 1/2? Well, that's negative 3/2. Then we have x squared plus 1. Now what's negative 1/2 minus 1? That's negative 3/2. Okay? And then what's the derivative? So multiply, what's the derivative of x squared plus 1? So this is just going back to the regular old power rule, which says, or excuse me, not even that. This goes back to the fact that we have a binomial here. The sum rule says, okay, we can take the derivative of these two terms individually. The power rule says the derivative of x squared is 2x, and the constant rule says that the derivative of a constant is 0. So this derivative here is just equal to 2x. And so let's just clean that up slightly. Let's say that's negative, okay, so we have negative 3 times 2, so let's say negative 6. Oh, you know what? I didn't even see that simplification. Negative 3/2 times 2x, that's just going to be negative 3x. Okay, times x squared plus 1 to the negative 3/2 power. Now, the last little thing you probably want to do is typically we don't leave answers with negative exponents. So what we would do here is say that this is equal to, let me draw that a little better, equal to, We can say, put a negative 3 up top, and then we could say x squared plus 1. We could either say to the positive 3/2 power, or we could, let's just do that first, positive 3/2. Or if you want to write it in radical notation, you could say negative 3 divided by, let's see here, the square root of x squared plus 1. X squared plus 1 cubed. Oh, either of these two last lines would be fine. But that's just in radical notation, and that's in just regular exponential notation. Okay. Let's see here. Now, I had an example that I wanted to look at. Let me see if I can find it real fast. Oh, here we go. Here's one where you have to use the chain rule in the same problem more than once. Let's see here. Let's change up colors. Let's say that f of x equals, let's say, sine cubed of 4t. Now, let's think about what does sine cubed of 4t mean? Okay, that actually means sine of 4t cubed. Okay? Now, it's really important for you to recognize what that means right there. That means this. So now we can use the chain rule, actually the generalized power rule, which says we have a function raised to a power. We can say that not f inverse, f prime of x, okay, we bring the original power out front, that's 3, and then we multiply by the inside function, sine of 4t. We raise it to the n minus 1 power, so 3 minus 1 power. Then we multiply by the derivative of the inside function, sine of 4t. So we have to do another derivative over here. So we have 3 times the sine of 4t. Now that is all raised. Oh, you know what? I could just do this. Sine squared. Actually, for the time being, I'll do it this way. Squared. Multiply. Now, what's the derivative of sine of 4t? The derivative of sine of 4t is, okay, it is the sine of 4t. But when you have a derivative of a trig function, and there's not just a single variable in the argument, that is, it's a composite. This is a composite function of sine of t and 4t. Okay, what you have to do, if you scroll way back up here, we haven't talked about this yet, but look there. If we have the derivative of sine of some function u is equal to cosine of u times u prime. So we have to take the derivative. Now, I messed up there. The derivative of sine is cosine. Somebody's probably thinking, what the heck are you doing? It's cosine of 4t times the derivative of the argument. So dx of 4t. Whew, this is a lot of stuff. So 3 times the sine. Now, sine of 4t squared, that's sine squared of 4t, times cosine of 4t, times the derivative of 4t, which if we remember the basic rules, we can factor the 4 out via the constant multiple rule. The derivative, oh, I should have said dt here. All right, guys, my notation's a little messed up here. That should be a derivative with respect to t, not an x right there. Okay, sorry about that. I'm just so used to using x as the independent variable. Okay, so this is 4. Oh, yes. Yes, 4. Let's see. Yeah. Cosine 4t, sine squared 4t, and then 4 and 3. Yeah, we're good. So all I need to do here is 3 and 4 is 12. Sine squared of 4t times cosine of 4t. And there we are. But notice it took 2 applications of the chain rule. And that happens a lot of times. You take a derivative, and because it's of how you have a composition structure, you have to use the chain rule twice. Okay? Let's see here. Let's do a tough one. I think I might call it the day after this one, but I want to pick another derivative, and I think I'm going to call it a day after this because this is going to be a long one. So let's see. Let's scroll down a little bit. Get a lot of space here. Oh, let's just go back to this. Let's just go back to this color. That's not a very good line. There we go. All right, let's take the derivative of a quotient that's raised to a power. Let me see if I can find it over here in the book. Oh yeah, there's lots of them. Let's see. We have a function. Yeah, this is going to be a long one. G of x is equal to a quotient, which is 3x squared minus 2 over 2x plus 3. And this entire thing is raised to the third power. Oh, I should draw better parentheses than that. Third power. So this is going to be tough because if you can kind of see what's going to happen here, the chain rule says, okay, we have a function. This entire thing, if you want to talk about the generalized chain rule says, or the generalized power rule says that if you have u raised to some power, then you can say, and you want to take the derivative, so the derivative of x like this, you can say n times u to the n minus 1 power times u prime. Now, n times u to the n minus 1 power, that's no big deal. But u prime, that's going to be the derivative of that, which is going to use the the quotient rule. Okay, so that's going to be a pretty long problem. So let's see. Let's start here. G prime of x. Okay, according to the generalized power rule. Oh, I'm going to need some more room. I did that too close. G prime of x is equal to, okay, it's 3 times my quotient, 3x squared minus 2, over 2x plus 3, raised to the n minus 1 power, so 3 minus 1 power, times the derivative of the inside function, so the derivative of 3x squared minus 2 over 2x plus 3. Now, this is going to take a little bit of work to do. Okay, so let's see here. Let's clean this up a little bit. 3 times 3x squared minus 2, 2x plus 3. Now to the 3 minus 1 power, that's squared. Now let's get some brackets going here. This is a quotient rule. So we're going to have to write a big fraction. Hopefully that's big enough. Now, the first thing you can always do with a quotient rule, so we're just concentrating on this right now, is we know it's going to be the bottom function squared on the bottom. So 2x plus 3 squared. Okay. Now let's employ the quotient rule. It says we take the bottom function, which is 2x plus 3, and multiply it by the derivative of the top, which is 3x squared minus 2. Then we subtract off the top function, 3x squared minus 2, times the derivative of the bottom function, 2x plus 3. Ooh, just had enough room. Okay, now we need to finish taking those derivatives. We still have this 3, and we have 3x squared minus 2 over 2x plus 3 squared. Let's still have these brackets. So we have 2x plus 3 squared still on the bottom. Now let's see if we can find those last derivatives, and the next after that it will be just simplifying. So we still have 2x plus 3. Now what's the derivative of 3x squared minus 2? Now this is a binomial, so we can take the derivative of each of those terms individually. So the derivative of negative 2, that's 0, but the derivative of 3x squared, now we can factor out the 3 via the constant multiple rule, then take the derivative of x squared. The derivative of x squared is 2x. 2x times 3 is 6x. Okay, so 6x, then we have minus, 3x squared minus 2. Now what's the derivative of 2x plus 3? Okay, that's a binomial again. So we can take the derivative of each term individually. The derivative of 2x is just 2, and the derivative of 3 is 0. So just a 2 there. Okay, and then now, this is just a matter of cleaning it up a little bit. I'm sure, let's see here. Now what do you notice about, we have 2x plus 3 here, and 2x plus 3 squared over there. So we can actually just go ahead and combine all the denominators and write that as 2x plus 3 raised to the third power. Now on the numerator, we're still going to have a 3. We'll have a 3x squared minus 2. Oh, I missed that. Oh, I made a mistake. We have a 2x plus 3 squared. We actually have, you think about the rules of exponents, we have a 2x plus 3 squared on the bottom here too. We have a 3x squared minus 2 squared, quantity squared on the top here. So I guess maybe I'll write that out. That's probably worth writing out another step here. We can write this as 3 times 3x squared minus 2 squared over 2x plus 3 squared. That's just using it's the quotient rule of exponents. Now let's see what else we have over here. Let's see, we're going to do some expanding, but the denominator is still 2x plus 3 squared. Now let's expand this. So we have 6x and 2x, so that is 12x squared. We have 6x and 3, so that is 18x. we have, let's see, 3x squared times 2, that's 6x squared, but then it's negative, so minus 6x squared. Then we have negative 2 times 2 is negative 4, but then it's going to be negative again, so that's going to be positive 4. Okay. I told you this was going to be long. So we have, we have a 3 times 3x squared minus 2 squared. Okay, now let's combine those denominators. Now, does it matter where? Oh, let's just put it here. That is 2x plus 3 raised to the 4th power. That's rules of exponents, because we have an expression where the base here is equal to the base here, and they're multiplied together. You can add the exponents and write it as a single base expression. So 2x plus 3 to the 4th power. Now we still have the numerator over here to deal with. Let's see, 12x squared minus 6x squared. So that would be 6x squared in total. Then we have plus 18x plus 4. Now, there's not really a whole lot left to do. I mean, I guess I could write it as one better looking fraction. I could just say this. I could say it's 3 times 3x squared minus 2 squared times 6x squared plus 18x plus 4 over 2x plus 3 to the 4th power. Now, I don't think, I could be wrong, I don't think if I expanded this top here, collected like terms, and then maybe factored again, I don't think that I could get anything to cancel out anywhere. Okay? So I'm not going to go any further than that because I don't think it's really going to make a difference. Okay? I think that's as good as we're going to get simplification-wise. But you always want to try to get it as simple as possible. But notice here, we were done with calculus at this step right here, but we had to take a couple steps to clean things up. And the algebra there was not trivial. Okay, so just be careful. There is a lot of algebra involved here, and there's a lot to it. Okay, now I said that would be the last one. Do we need to encore? Anything else I want to do here? I guess I can save logarithmic for another day. Let's see if there's another interesting one I'll do before we leave. Let's do an application. I said I wouldn't do an application, but let's do an application. Because I like this one here. Let's see. So this is going to be an application. Here's an application because we need some context to all this. We need some context. Let me see here. Let me see if I can find something interesting. Maybe, let's see here. Now, you know what? I know what I want to do. We haven't done a second derivative. Let's see if we can find a second derivative type question. Let's see here. There we go. I think. Where's the interesting questions? Sorry guys, I'll have one just half sec for us. I wasn't planning on doing one of these, but I think it'll be interesting. Yeah, here we go. This is actually, this is one out of the book I'm looking at. This is the Larson book, if you're not in my class. This is the Larson Transcendental 6th edition, but here's one. And it is on page, let me see here. 134. Okay, I'll change it up a little bit. It says at time t, a diver jumps from a platform, diving board that's 32 feet above the water. Oh, let's change it up. Let's say the diving board's pretty high. Let's say there's a diving board, diver jumps from, let's see, 100 feet up. Okay? The position of the diver is given by the position function s of t equals negative 16t squared, plus 16t plus 100. Okay? Now, we haven't talked about this in this video, but in class we've talked about, if you take the derivative of your position function, which is s of t. So we talk about these in algebra class, that you have a position function. Here's a quadratic position function that you could substitute for different values of t and find the position of the diver, the height of the diver, at different values of t. Okay. Now we could figure out, say, where the diver, how high the diver is at t equals 1 second or t equals 2 seconds, and t is measured in seconds here. Okay. So let's see, what could we ask here? Let's ask a couple questions. First of all, when does the diver impact the water? First question. Second question. What is the velocity of the diver at that point? And then here's the last thing. What is the acceleration of the diver at that point? Now, here's the thing. To get velocity, we take the first derivative of the position function. That'll give us a velocity function. To get the acceleration function, we take the derivative of the velocity function. So s prime of t is the velocity function. Okay, let's see what that is. Okay, this is a polynomial. Let's take the derivative of each of those terms individually. So let's see, we have, according to the sum and difference rule, we can take the derivative of each term individually. So we could say that this is negative 16 times d of t squared plus 16 times d of t plus the derivative with respect to t of 100. So I took the derivative with respect to t of each of those terms. Well, this one just turns out to be, that's 2t. So I have negative 16 times 2t plus 16. What's the derivative of t? That's just 1. What's the derivative of a constant? That's 0. So here that's negative 32t plus 16. Okay, so that's our velocity function, s prime of t. Now, if we want to find the acceleration, we take the derivative of velocity. So there is velocity. Let's take s prime of t. Now, second derivatives is just you take the derivative of your first derivative. So here, same thing. We can say that this is negative 32 times the derivative with respect to t of t plus the derivative with respect to t of 16. Okay, so it's negative 32. What's the derivative of t? Well, that's 1. What's the derivative of a constant? That's 0. So the acceleration function is negative 32. So that's acceleration. S double prime of t. Okay? Well, that answers the last question for us because guess what? Acceleration is constant. There is no t in here, which means acceleration is the same no matter where. Now, I should say that is feet per second squared is the units there. And the units here are feet per second. Okay. Let's see here. So let's answer the question. So the third question, that's the easiest. The acceleration doesn't matter at what point he is, he or she is. It's negative 32 feet per second squared. Okay, so it doesn't matter if it's the point of impact or wherever, 32 feet per second. Now, what is the velocity of the diver at that point? I should say negative 32 feet per second squared. That's just the acceleration due to gravity on Earth. Negative 32 or feet per second squared or negative 9.8 meters per second squared. Okay. That's because the diver doesn't have, some sort of propulsion device pushing him down. It's just gravity pulling him down, which acceleration due to gravity is negative 32 feet per second. So if you had known that, you could have answered already. Now, what's the velocity at the diver at the point of impact? Now, we don't know what the point of impact is. So that's algebra class. Off to the side, we have to do some algebra. Now, how do you find the point of impact? Well, s of t, that gives us position. If we set s of t equal to 0, that's going to give us the point where the height of the diver is 0, also known where the height of the diver is hitting the water. The height is when it impacts the water. So we could say that set s of t equal to 0 to find when diver impacts water. Okay? So we could say negative 16t squared plus 16t plus 100 equals 0. Okay? Now, to solve this, that's just a quadratic equation. Now, I shouldn't have picked 100 there. I should have picked a number that was divisible by 16, so the quadratic equation would be a little easier. But I didn't. I wasn't thinking that far ahead. So what I'm going to do is I'm just going to solve this real fast off to the side. Again, I'm just going to use the quadratic formula real fast, not to waste a bunch of time here. So let's see here. Let me look for my calculator real fast. Okay, here we are. So we have the coefficients are negative 16, 16, and 100. Now, okay, I'm getting an irrational number here. That's fine. I think it's irrational. Let me check. Negative 2, let's see, no, 3.0495097757. Yeah. So I get, with a quadratic, you get two answers, but one of the answers is negative, so we have to toss that out because he's not going to strike the ground in negative time. It has to be the positive root here. So t equals 3.0495097 5/7. Okay? So there's the time when the diver impacts the water. Okay? So he jumps off the diving board 100 feet up. Maybe he's a cliff diver, so it's not a diving board, it's 100 feet up. And it takes a little over 3 seconds to impact the water. Now, to find the velocity at the point of impact, we just evaluate s prime at this t value. So s prime of 3.0495097757 equals, okay, sorry about the space here. We just plug into this function here. So it's negative 32 times that t value plus 16. I'll use my calculator real fast. So negative 32 times that number that's barely over 3 plus 16, and I get the velocity. I won't say equals, I'm going to round here. I should, round, that's approximate there too, is approximately negative 81.6 feet per second. So that is velocity at point of impact. Now, if you wanted to find the velocity at any other point in time, you could just plug into this velocity function, the first derivative of the position function. So if you say you want the velocity, at time equals 1 second, or 2 seconds, or at 3 seconds, right before impact, you could just evaluate this velocity function at that t value. Okay? So, applications are important. We'll see lots of applications, especially as we get to the section on related rates. That'll be all applications. Chapter 4 is all about things you can do with derivatives as well. Things like finding maximums and minimums and concavity and stuff like that. Okay? So don't be afraid of the applications because they will be throughout the course. And here's just one basic one. Now it's very important. We will oftentimes have position functions like this right here, and then we'll differentiate to get a velocity function, then differentiate again to get an acceleration function. And then once we get to integration later on towards the end of the semester, we might do something like start with an acceleration function and work backwards to get a position function, okay, given certain constraints. So, at any rate, I hope this has been somewhat useful to you. We did a handful of derivatives here. Most of them were just introductory, nothing too terribly hard. But I hope that this helped you out. I also hope that doing each little step, how the notation works. I hope that that is good for you too, because using correct notation is certainly important, and you don't want to be mixing up the dx's and the primes and all that kind of stuff. So if you have any questions about that, just let me know. You guys have a good weekend, and feel free to email with any questions you have or bring questions you have to class. Talk to you soon.